6.5. Section 6.5 is we're going to look at some of the properties of definite integrals, and then also practice definite integrals more along with the substitution. So I just want you to think about the definition of the definite integral, which is the limit of a sum as n approaches infinity, here for I from 1 to n of f of xi delta x, where this is actually the sum of the areas of those rectangles. And here, when we take the limit as n approaches infinity, we are increasing the number of rectangles up to infinity. And also geometrically think about it. If you have a function f of x, and these are the two vertical lines, x equals a and x equals b, and a and b are the limits of the integral, then what we have here is this area. Okay, so now let's look at these properties of definite integrals. If you have two functions f and g that are integrable functions, and integrable simply means that this limit exists. If this limit exists, then this integral is, you're able to calculate that, yes? So you call that integrable. So if a function is integrable, f and g are integrable, then you have integral from a to a of f of x dx is 0. So if the upper bound and the lower bound are the same thing, integral of f of x dx from a to a. So in that case, you're trying to figure out what the area of a line is, yes? Because there would be no area. It would be just a line. And we know that the area of a line is a one-dimensional object. The area of that is going to be 0. The other property is integral from a to b f of x dx is if I swap a and b, I'm going to get minus integral b to a f of x dx. So by swapping the bounds, by swapping the lower and the upper bounds of the integral, I am negating the value of the integral. And this simply happens because if you think of delta x, the definition of delta x is b minus a over n. If I swap a and b, I'm going to get a minus b over n. And that a minus b over n is the negative of b minus a over n. So if I just swap, I get a minus b over n, which would be negative delta x. So that's the reason this property happens. If you just swap the two bounds, a and b, then delta x becomes minus delta x. So the new integral is going to be minus the old one. So for example, integral from 2 to 3 of, let's say, x squared dx would be minus integral from 3 to 2 of x squared dx. So algebraically, it's simply because of this. Any questions so far? The third property is if you have integral, you remember we had this for indefinite integrals, we would say that this is actually c times integral of f of x dx. And this is also true for a definite integral from a to b c f of x dx. And the reason that's going to be c integral from a to b f of x dx. And the reason that this is the case is this is going to be limit as n approaches infinity of a sum I from 1 to n of c f of xi delta x. And this c, since I since this c here is a constant with respect to the I, and this c here is a constant also with respect to n, so it goes out here and then completely goes out of the limit. That's why you can just move it out of the integral sign. The fourth one is if you have integral f of x plus g of x dx. You remember for indefinite integrals, which are basically antiderivatives, this is integral of f of x dx plus integral of g of x dx. And if you have a minus, it's going to be minus that. So these properties that you had for indefinite integral, you also have it for definite integral. So if you have bounds a to b, a to b, a to b, you still have this property. So the sum of two definite integrals, the sum of the definite integral of a sum would be the sum of the definite integrals, or the definite integral of a difference would be the difference of the different integrals. Notice that this is not true for the product. So this is not at all the case. So this is not equal integral of f of x times integral of g of x. That's not at all the case. And with bounds or without bounds, in the case of definite or indefinite integrals, we do not have this. But with sum and difference, we have this property number 4. And finally, property number 5 is easier to understand in terms of areas. If you have a function, f of x, and let's say that ab, so if I just think of a number that is between a and b, for example, the number c that's here, then you agree that this area, the whole area from a to b, is actually this area from a to c plus this area from c to b. The whole area from a to b I can write as integral f of x dx. So this is going to be integral from a to c f of x dx plus integral from c to b f of x dx. So this property number 5 basically says that this area, the whole area from a to b, can be divided into two sub areas, from a to c plus from c to b. But the thing is, here it says that c is between a and b, but actually, algebraically, it's possible to prove that this is true for any real number. So c does not have to be between a and b. If c is less than a or greater than b, also still this works. But again, it's much easier to understand it in terms of the geometry of the areas of the regions. Any questions? Okay, so now that we learned about these properties, let's just combine whatever you learned about substitution and definite integrals. So if I just give you this, if I give you x times root 9 plus x squared dx, and I ask you to solve this, you say, okay, this is an indefinite integral. I can solve that by substitution. I take u to be 9 plus x squared. Then du is going to be 2x dx. Then I'm missing a 2, so I multiply by a 2, I divide by a 2. And this will become what? This will become 1 over 2 integral of u to the power of 1 over 2 du. I know how to do this. This is 1 over 2 times u to the power of 3 over 2 plus c, 2 over 3. So it's going to be 1 over 3 u to the power of 3 over 2 plus c. And that is going to be replaced, the u, by 9 plus x squared, and I'm done. So you would do this. This is substitution. Now, what if I give you a definite integral like this? Integral of x times 9 plus x squared dx from 0 to 4. Then you say, okay, this is going to be whatever f of x is, where f of x is the antiderivative, an antiderivative. One antiderivative of this function here, evaluated at 4, evaluated at 0, and then I need to subtract whatever f of 0 is from f of 4. Yes. So this is something that we learned about definite integrals. This is called the fundamental theorem of calculus. It is just telling me that in order to figure out this area, the only thing I need is one antiderivative of this function. One antiderivative of this function. I can evaluate that antiderivative at the upper bound minus the antiderivative at the lower bound. Okay, and I have one antiderivative here. So imagine c is 0. I have one antiderivative. So this is going to be 1 over 3, 9 plus x squared to the power of 3 over 2 from 0 to 4. So I have to evaluate that at 4. I have to evaluate that at 0 and subtract. So if I plug in 4 into this, let's see what happens. I'm going to get 4 squared is 16. 16 plus 9 is 25. Root 25 is 5. 5 to the power of 3 is 125. So 125 over 3 minus. If I plug in 0 into this, I get 9 to the power of 3 over 2. 9 to the power of 1 over 2 is 3. 3 to the power of 3 is 27. So I get 27 over 3. So it's going to be 125 over 3 minus 9. So I'm going to get 98 over 3. So that was one way of doing it. Did I do it correctly? Yeah, 98 over 3. Any questions? Maybe I should explain how I got the 125 over 3. If I plug in 4, I get 25 to the power of, you see, 4. If I plug it in here, I get 16. 16 plus 9, 25. So how do I simplify 25 to the power of 3 over 2? Notice that this is like having root 25 to the power of 3. That's going to be 5 to the power of 3, so 125. So that's why. Is this clear? Okay. Basically, I'm using this. If I have, let's say, x to the power of m over n, we know this is the same as having x to the power of 1 over n, that to the power of m. That's the same as having the nth root of x to the power of m. So if I have 25 to the power of 3 over 2, I can write that as 25 to the power of 1 over 2, the whole thing to the power of 3, which is like having root 25 to the power of 3. So that's how I got 5 to the power of 3 is 125. So that was one way of doing it, because you have one antiderivative. And the moment you have one antiderivative of this function, you can just calculate the value of that antiderivative at b minus the value of that antiderivative at a. And using the substitution technique, you can get an antiderivative of this. So that was one way of doing it. There is another way of doing it, which I recommend, and it's like this. So for the problems that you're solving for this type of definite integrals, I recommend that you do this. First, you realize that this needs substitution. This integral needs substitution. So you would take the substitution u equals 9 plus x squared, and then du is 2x dx. Yes. The other thing that you do is you try to change the bounds accordingly. So you say x, because this integral at the beginning is in terms of x, and x is supposed to change from 0 to 4. If x changes from 0 to 4, how would u change? This would be the new bounds. When I plug in 0 into this, I'm going to get 9. And if I plug in 4 into this, 4 for x, I get 16 plus 9, that's 25. So u is going to change from 9 to 25. That is, if x changes from 0 to 4, u, because of this definition of u, is going to change from 9 to 25. Okay, now I do whatever I need. I'm trying to create this du, so I multiply by 2, divide by 2. This is going to be 1 over 2 integral of root u du. And now, rather than using the 0 and the 4, since I have substituted x with u, I'm going to use the new bounds from 9 to 25. And then I solve this. So this is going to be 1 over 3 u to the power of 3 over 2 from 9 to 25. So I get 1/3 of 25 to the power of 3 over 2 minus 1/3 of 9 to the power of 3 over 2. I'm going to get the exact same answer. Yes, so this is 125 over 3 minus 27 over 3, which is going to be 98 over 3. But it's easier to do because you don't need to go back to x. As you change your variable from x to u by doing the substitution, at the same time you're changing the bounds, the lower bound and the upper bound, so you never have to go back to x. You just solve this easier definite integral. Is that clear? Any questions? Okay, one more example. Integral from 0 to 2 of x e to the power of 2x squared dx. Okay, for this one I will have to take u to be 2x squared, then du will be 4x dx, and when x changes from 0 to 2, u would change from 0 to, if I plug in 2 into this, I get 8. 2 to the power of 2 is 4, 4 times 2 is 8. So this becomes integral, and I see that I'm missing a 4 here. I have the x, but I don't have the 4. So multiply by 4 here, divide by 4 outside, get 1 over 4 integral of e to the power of u du. The 4x dx is going to be du. And I'm using the new bounds now from 0 to 8. This is 1 over 4 e to the power of u from 0 to 8. So it's going to be 1 over 4 times e to the power of 8 minus 1 over 4 e to the power of 0. So that's e to the power of 8 over 4 minus 1 over 4, because e to 0 is just 1. It's going to be e to the power of 8 minus 1 over 4. That's the answer. We're good? Any questions?
I
Yes,
have a question. Yes. What is the symbol between the E and the U?
the
Is it
sim. Oh, I just,
that
it's my
is
board. That's a
yeah.
DU.
Okay.
That's the 4x and the dx, which become du. Any other questions? Okay, let's do the next one. Example 3. Definite integral from 0 to 1 of x squared, x to the power of 3 plus 1 dx. I'm going to take u to be the denominator. So u is x to 3 plus 1. Then du will be 3x squared dx. I am missing the 3. So, and x changes from 0 to 1. What would happen to u? The u would change from, when I plug in 0 into this, I get 1. If I plug in 1 into this, I get 2. So it's going to be 1 over 3 integral from 1 to 2 of the numerator would be du, the denominator will be u. So it's going to be ln of absolute value of u, 1/3. 1/3 of ln of absolute value of u from 1 to 2. So it's going to be ln of 2 over 3 minus ln of 1 over 3. But this is just 0. So the answer is ln of 2 over 3. Ln of 1 we know is 0. We're good? Any questions? Okay, so next we have finding the area under the curve. We know that these integrals, these are basically areas. So this is an area under the curve above the x-axis between the two vertical lines from x equals 0 to x equals 1. So we know that. So sometimes the problem is given to us in the form of a geometry problem. So we are asked to find the area of the region under the graph, under this graph from x equals -1 to x equals 1. So for this number 4, example 4, which is asking us for the area of a certain region, since it says that f of x is e to the power of x over 2, and we're given the two vertical lines, x equals -1, x equals to 1, we know that we are actually looking for this. This is the area under the curve e to the power of x over 2 above the x-axis, and between the two vertical lines x equals -1 and x equals 1. So is that clear? And then we solve this. We take u to be x over 2, then du is going to be x 1 over 2 dx. I can multiply it by a 1 over 2 inside and by 2 outside. Also, I noticed that when x changes from -1 to 1, u would change from -1 over 2 to 1 over 2. So this is going to be 2 integral from -1 over 2 to 1 over 2 of e to u du. So it's 2 e to u from -1 over 2 to 1 over 2. So it's 2 e to the power of 1 over 2 minus 2 e to the power of -1 over 2. So if I need an approximation for that, I can, oh, what happened here? 2 e to the power of 1 over 2 minus 2 e to the power of 1 over 2. I'm just plugging in 1 over 2 into this minus negative 1 over 2. I plug it into that. I can factor out the 2, and I get e to the power of 1 over 2 minus e to the power of negative 1 over 2, which I can also write as 2 root e minus 1 over root e. I can also write it in this form. If I need, in the web work or in the test, you would just plug in this, but in case we need an approximation rounded to a certain number of digits after decimal point, you can use a calculator. And in this case, if you round it to 2 digits after the decimal point, in other words, if you round it to the nearest hundredth, you're going to get 2.08.